So good morning, everyone. My name is Nicolas Nino, and I'm a PhD student for the University of Georgia. And it's my pleasure to be here presenting this work on behalf of my collaborators. So we all know that IoT devices are very popular nowadays. We have security cameras, smart locks, bulbs, etc., which are integrated in our daily routines. Unfortunately, security issues remain an issue and a problem to the end users' privacy, security, and comfort. So it is imperative to study IoT security. Now, IoT devices communicate with companion mobile apps, allowing the user to control the device through their phone and serving as a bridge to the developer server when needed. The firmware of a device is vital for the functionality of and the security of IoT systems. Therefore, studying the security properties of IoT devices requires thorough firmware analysis. However, collecting bare metal firmware is challenging due to the lack of vendor repositories, unlike with Linux devices. As a result, the security of bare metal devices is less understood, despite their importance in the IoT ecosystem. The absence of firmware has led researchers to focus on analyzing mobile companion apps or the network traffic between the device and the server to infer the security properties of corresponding IoT devices. Unfortunately, these approaches cannot reveal low-level features critical to the security of devices, such as memory corruption bugs or the implementation of attack mitigations. There is work focusing on firmware analysis. However, the datasets used in these studies are collected in ad hoc ways and are not suitable for comprehensive security analysis. X-Ray, for instance, collects only Nordic and Texas Instruments firmware for BLE-based devices. This GitHub repository, which is a compilation of various works, contains only ARM firmware. Hallucinator collects firmware from 3 vendors by compiling examples from their SDKs. So these datasets consist of a small number of firmware images that overrepresent certain sectors of the IoT ecosystem, are collected using methods that are difficult to scale or generalize, or collect firmware that do not necessarily represent real-world devices. So our goals for this project are: first, gather an extensive bare metal firmware dataset to offer the community a diverse resource for studying the security of IoT ecosystem. Decompose the IoT market to identify the most popular vendors and architectures, and perform a scalable and general security analysis on the collected images. But before discussing our approach, let me briefly review the different methods developers use to update IoT device firmware. First, we have the over-the-air method. So when a new firmware is released, the developer places it on a server to be requested by the companion app, and then the firmware is sent to the device from the phone. In the second method, the new firmware is included in the files of the latest version of the companion app. So recognizing the companion app's crucial role in the firmware distribution, we focus on collecting firmware by analyzing the app's logic, focusing primarily on the first method, but we also leverage the second method inspired by X-Ray's approach. So this is the high-level workflow of our approach. Step 1, collect a database of APKs that connect to IoT devices. Step 2, recover the URLs to download firmware. 3, download the firmware. 4, identify the bare metal firmware and unpack the information needed to perform the security analysis. Okay, now let's dig into details of our approach. With around 2.3 million mobile apps in the Play Store alone, we focus on those that connect and control IoT devices. Leveraging prior research, we selected over 40,000 unique companion apps for analysis. Specifically, IoT Spotter uses machine learning to identify IoT apps, and 2 other studies use manual work to compile the mobile IoT apps. So we combined these datasets and removed any overlaps, and this is the initial input of our work. With the APKs, we can now recover the download URLs. So to recover the firmware, we must reverse engineer the app's code and reassemble the URL components. We chose to tackle this problem using backwards value set analysis, a technique that efficiently determines the set of possible values at various points in the program. At the bottom, highlighted in blue, we can see the call to a URL constructor using the register R2 as a parameter. So we are interested in determining the value of R2, as it contains the URL used to download the firmware. As we move backwards through the code, we identify points where the value of R2 is modified or constructed. And upon reaching the top of a function, we search for calls and resume analysis from those points, as each call represents a different branch and potentially a different URL value. After retrieving the definition of all key variables using the URL construction, we obtain all the components and the sequence required to reassemble the URL. So we proceed with the forward simulation, executing the statements in the correct sequence to reconstruct the value of R2. Once we have the reconstructed value, we're ready for the next step in our workflow. But before proceeding, let me briefly show you some of the challenges we encountered with previous VSA approaches. We found that apps often retrieve information like device type, hardware version from the device to reconstruct the URL, because a single APK can connect to multiple devices. However, since we want a scalable approach and are conducting static analysis, we cannot communicate with the device and thus cannot recover this information. Interestingly, we found that the same global variable is sometimes used in various parts of the code and compared with hard-coded values to make decisions, because the app logic may vary depending on factors such as device type. This is great news because we can use this information to infer the value of this variable. And to achieve this, we implemented symbolic execution. We face challenges also with libraries like async-task and frameworks like Android's intent, which can create gaps in the control flow graph and lead to incorrect URL reconstructions. Previous value set analysis methods did not fully address these gaps, so to improve upon existing approaches, we enhanced the handling of these missing edges, resulting in a more accurate reconstruction. So after reconstructing the URLs, our next task is to download the images using the various found distribution protocols, such as HTTP, FTP, and MQTT. But we found that firmware downloads often involve an intermediary text file, which serves as a distribution point for the images. Typically, the reconstructed URLs points to a JSON file, from which the app fetches the firmware URL before downloading it. This method is common because it allows developers to update the firmware by modifying the file's contents, rather than the entire app. So we approach this as a crawling problem, recursively searching for links in the response's content. Some FTP URLs have credentials embedded directly, while others store credentials in unstructured text files, as shown in the example. Identifying information within such text can be challenging, so we use prompts for Ollama's large language model to convert the text into machine-readable format. At this point, we have collected tens of thousands of files. Despite applying filters during the collection process, we expect a high rate of false positive due to the nature of crawling. So we need to identify the bare metal firmware from the downloaded files. Well, we noticed that there are signatures left in the firmware by the compilation and packaging processes that we can identify and leverage. We found that there are 4 distinct categories of signatures identifiable in a firmware image: SDKs, encoder, bootloader, and architecture. SDK artifacts. So vendors offer a collection of software development tools designed to accelerate the firmware development process for their chips. Most SDKs create a header for the firmware images, which is useful for validation. By examining the header of a firmware image, we can determine if it matches the fields defined by a specific SDK. Encoding artifacts. So sometimes images are not transported or stored in the regular binary representation before being flashed into the device. Instead, they're presented in an encoded text format. Bootloader artifacts. We have observed that open source bootloaders are occasionally used to package the actual firmware, which significantly simplifies the firmware distribution process for developers. Similar to SDK signatures, we utilize the header that these bootloaders add to an image. Architecture artifacts. Distinctive signatures are added to a firmware image by the architecture as well. In the case of ARM, we use the vector table as the signature to match. It must include the initial stack pointer at position 0, followed by the vector table entries with their least significant bit set to 1. So in total, we have developed 39 different artifacts so far. Signatures are valuable not only for identifying firmware, but also for extracting metadata crucial for firmware analysis. For instance, using Ghidra, specifying details like the architecture, the base address, the memory map significantly improves the accuracy of the disassembly and reduces manual effort. In this graphic, we can see the process numbers throughout the previous steps. The blue line corresponds to images collected using the first method of firmware distribution, OTA, while the red line corresponds to images collected using the second method. In the end, we've got 3,692 unique images. Here we can see the majority of the images are ARM Extensa architectures, and the most popular vendors are Nordic, TI, Espressif, and T-Link. So due to a popularity in the market, we selectively conducted static analysis for the collected ARM and extensive firmware. The first case study for firmware analysis is the detection of end-day vulnerabilities. To reduce time to market and streamline firmware development, it is common practice for device manufacturers to integrate open source middleware, RTOS libraries, and chip SDKs into a firmware stack. Uncovering these libraries used by firmware image is important because if a library contains a vulnerability, the firmware image is likely to be vulnerable as well. Then we first compiled a dataset of libraries commonly used in bare metal IoT devices. And to determine if an image uses a specific library, we first perform a function matching procedure. If we find at least two similar functions between an image and a library, we conclude that the image uses the library. With this method, we found that 191 images from 31 different device manufacturers are vulnerable to a total of 14 unique CVEs. The second case study is the detection of the implementation of attack mitigations. To prevent attacks, various mitigations have been developed. If these mitigations are not included or correctly configured, the image remains vulnerable to issues that could otherwise be prevented. These mitigations include the memory protection unit to protect sections of memory from unprivileged access, trust zone technology to protect high-value code and data, stack limit feature that prevents overrun of stacks, and stack canary, used to detect a stack buffer overflow before the execution of malicious code can take place. To be able to identify these features, we developed checks for each mitigation. Unfortunately, we found that these mitigations are very rarely adopted in the real world, with MPU being used 1.56%, stack canary 0.11%, and the other two mitigations not being used at all. So in conclusion, we present a novel approach for the large-scale collection and validation of bare metal IoT firmware. We present an extensive bare metal firmware dataset to offer the community a diverse resource for studying the security of the IoT ecosystem. And we present the results of our general security analysis demonstrating the lack of firmware protection, existence of end-day vulnerabilities, and rare adoption of security mitigations. Finally, you can find our tools in our GitHub repository. Thank you.